everybody. It's a pleasure being here today. I wanted to give you a little background quickly, how we have this background on the historic fabric at Stanford. Our company, Architectural Resources Group, has been working with historic buildings for over 40 years. That's the focus of our practice. About 20 years ago, one of our clients said to us, you know, you help us with the design. We have to have you there all through the construction. Why don't you just be my contractor? And that's how we started our construction company. And we've continued to work for Stanford as architects and as contractors for the past 20 or 30 years. So what I'm going to talk about today is tile and concrete. Tile of the roofs at Stanford and the historic pavement that we see throughout the quad. Earlier, Sapna showed us photographs in Venice of the checkerboard pattern, the red and the gray that we see in that beautiful city that we believe served as the example for what we find at Stanford. We're also going to talk about the tile. That is really a very important character-defining feature. And what is the link between those two materials? Where they are both materials that are in a plastic state, right? And then they can be shaped into any type of forms, and we see that all over the campus, right? As far as the clay tile, they're kind of a traditional form as the clay tile, and you can see here, it's used all around. And as the concrete, we're going to talk a little bit about the concrete and how Stanford really is one of the milestones in the development of the use of concrete and reinforced concrete in the United States. All right? So, concrete is a ubiquitous building material that now we see all around the world. And many of you have traveled and seen concrete and used in a very utilitarian way and in a very creative way. Recently, in the last 100 years, architects have thought of concrete, and it's been a progression in thought, and seen it as a respected material of its own. And so we can see that here at Stanford too, where perhaps the form boards are left in the concrete imprint, or concrete is used as cast stone, and we're going to show you an example of that. So let me start to talk a little bit about the clay tile at Stanford. We have here an example of the advertising literature that Gladding McBean produced. Sapna spoke earlier about Gladding McBean and the relationship between Mrs. Stanford and Gladding McBean. And it reminds me of a story, and that was a personal relationship. But there's another part to that. I was discussing with one of my good friends and consultants, Hank Dunlop, who's an expert in California historic interiors. And I said to him, you know, Hank, we were working on a property that was way out on the remote section of the California coast, and there we found this very expensive wallpaper. And I said, well, how did it get out there? You know, it's the 1840s or 50s, it's way out in the middle of nowhere. How do we get that historic fabric, that interesting material out there? And he said, David, you have to remember one thing. Follow the money. Follow the money. And so I think we have to remember that here. We have some very amazing high-quality building materials. We have traditional sandstone building, but innovation. And it's all about following the money and what was available. The clay tiles at Stanford, as we talked about, were produced by Gladding McBean. Here you're going to see an example of the typical tile roofs throughout the quad. This is Gladding McBean's excerpts from their promotional material showing specifically Stanford buildings. That's no coincidence. Stanford was one of their best clients, right? And so in that context, the red clay tile became a standard here, and Gladding McBean on their end were making sure that Stanford remained an important client by retaining the historic drawings, by retaining the colors that were used for the tile, and in just keeping a close contact. I'm going to talk about the Hoover Tower, which you can see right over here. As we progress through the years at Stanford, that historic kind of barrel type of tile was reinterpreted. And here you see the top of the Hoover Tower, where we have these scallop-shaped tiles. These are the drawings that were produced, because as you go up toward the top of the tower, they change size, all right? So an innovation of a traditional material, a plastic material, into another shape rather than the barrel vaulted tiles. The precedent, of course, for the barrel vaulteds were the California missions. And here we see another precedent in the history of architecture from Europe. We recently completed a project with Stanford for the repair of the ball finial that was hit by lightning. Now, early in my career, I had the opportunity to undertake a restoration of Hoover Tower in the 90s. And at that time, as we do with all our projects, we finished with a report on the building and what we had done. And we recommended that the building receive and be fitted with a lightning arrest system. It was not done at the time. Fortunately, we had in writing that we had recommended this, so that when we came back to do the project, we were not held responsible for this particular strike. As part of this project, we did put in a new lightning arrest system. It was a large rod, put 6 to 8 feet above, through this pipe into a new ball finial, and the cable was run down into the building. We had to do this very carefully. We had a special engineer who only designs lightning arrest systems, who came and made sure that there are no bends in the cable that went down all the way into the basement, where it went down several feet down through the foundation. But what I'd like to point out here is, here you see a reinterpretation of concrete. This is cast stone, cast into a decorative cladding material that is used on the top of the tower and at other locations for protecting the reinforced concrete that is inside. So cast stone, reinforced concrete, and here you see the clay tile that was damaged as the ball finial pieces came falling down. At that time, we repaired this. Rather than pull up all the tiles, the repair at this point was to patch these areas and wait for a further restoration. We've had 2 restorations in the last 30 years, and in both cases, the way that was done is we went up to the observation tower, and steel beams were extended out from the observation tower. Up from that location, a scaffold was placed, because a platform was placed on the steel beams. And then below, those steel beams supported a swing stage scaffold that could go up and down the outside of the building. And that's how the building was accessed. This most recent one, we accessed the ball finial with a crane and a bucket and it's one of the largest cranes in the Bay Area that we use to access the top. The clay tile is a product that does not deteriorate, we found here, so we can salvage it. And when we re-roof, it's the membrane underneath that needs to be replaced, not the tile itself. There is some breakage, usually 20%. And so that's because of along the ridge and in other locations, the tile is mortared into place. So those tiles are lost. When we re-roof and we have supplied new tile, we mix them in with the old at random so that the differences are not noticed. And then the membrane is replaced and the roof goes back. And so what's wonderful about the clay tile is it can be reused and reused and reused. And we really haven't seen much deterioration even from the beginning of the tiles. Well, sometimes we've had to clean, and we want to be cleaning. We want to be careful with the cleaning because we don't want to push any harsh chemicals up to reach the membrane underneath that could cause deterioration. So we like to stay with a hot water rinse, and that's basically how the tiles are cleaned. It's power washing, but at a low pressure, right? Because we really don't want to force too much water up under the roof. So I'm going to shift from clay tile, and we can talk a little bit about that later, about the actual treatments, but I want to give you a little history of pavement. And this is a photo of San Francisco in Washington Street. The 1880s, the streets are cobbled, but the sidewalks are wood. What's the problem with wood? Well, you can imagine, many of you have decks at home. You know how rapidly that wood deteriorates. And so you had a bustling city that was trying to expand, and the sidewalks were a real problem. So there were many entrepreneurs that developed techniques for producing sidewalks that were safe to walk on and durable. And here you see an example here of a historic sidewalk with reinforcing. Now, the individual who was the most prominent and historical in the development of concrete was Ernest Ransome. Ernest Ransome was a Californian, and the development of reinforced concrete happened in Northern California. It did not happen on the East Coast. It happened here, all right? Portland cement came to the West in the 1880s, and it was at that time that Ransome started to develop the twisted reinforcing bars that were used eventually in many buildings. The impetus for that was, of course, that San Francisco had earthquakes, and they knew that buildings, just brick buildings, would move and were unsafe. So Ransome developed this type of system of reinforcing. This is the first reinforced concrete structure in the United States and probably the world, in Golden Gate Park, Alvord Bridge. And of course, the Stanford Museum, the Cantor Center, is the first monumental reinforced concrete building in the world. All right? So Ransome's work here, what we find in these early works is that the reinforcing bars are in the horizontal position. They're in the floor slabs. They're in the roadbed. That's where they felt that they would be of the most use. Eventually, they begin to be used in the walls. Right here, the most recent restoration, we found that these buttresses, these wing walls, did have some reinforcing, but they were wire, just very thin wire that followed the curvature of the wing wall. And we found this also in the museum when we restored the skylight. The ribs of the skylight, also reinforced concrete, had wire reinforcing. So interesting to see that same technique being used around the Bay Area. And here you can see some of the historic twisted rebar that we found at Alvord Bridge. So what does that have to do with Stanford? Well, we had this same problem. We had arcades and paved areas surrounding the historic masonry buildings, and we had George Goodman's artificial stone. Note that what he's doing is imitating stone, imitation of stone. And just so as we saw those photographs in Venice of the marble checkerboard arcades. Here we're trying to imitate that with concrete. It's an early photo of the installation of the pavement. And what's important here is that we can actually see the tar paper that was used between each unit, all right, that allowed them to move independently. Very important component. Okay. So we've undertaken a long-term program with Stanford to make sure that when the pavement is replaced, it's done in a way that matches the original historic fabric. And why did we need to do that? Well, we had natural causes. We had cracking. We have clay soils underneath the property that Stanford is built on. We had staining. We had very poor matches, as you see here. And we had a little bit of settlement. So the impetus for all of this was when the seismic upgrade of the quad occurred. And each of the buildings was upgraded. The design work was done by a different architect and by a different engineer and by a different contractor. Everyone had different ways of matching the historic pavement or pavers that they had to take up to put structure underneath. And so that's why we've got these patterns of mismatched pavement. And so the university, seeing this happening, decided that they wanted a standard. And the standard is something that we worked with them to develop. We began by taking the historic pavement and in our laboratory, breaking it down into its constituent pieces. And so that included the sands, the different aggregates, the pigments, and the type of cement that was used. So here you see the different constituents. You've got the sand, the cement, and then we went to the test samples. Now, and of course the pigments as well. This looks like an easy process, but finding the type of sands to match the original was very difficult. We had to go, we first found sands in Russian River that were a good match, and then that quarry closed. And through the last 20 years, we've had to come up with different combinations of materials that will still work and give us a match to historic pavement. We had the pigments all figured out, and then the company that supplied those in San Francisco closed. So once again, we had to go back to the drawing board and find new pigments that would work in formulating the mix for the historic concrete. Now, you would think that a simple material that includes cement, sand, pigment, and water, 4 constituents, would be very easy to reproduce. But we found that there were so many factors involved. How thick the mix was, what the temperature of the water was. Everything contributed to either getting the color right or not getting it right. And so that's why it's been a long process, and trying to maintain the consistency throughout has been a challenge. Here you see the samples that Stanford all these years has maintained, the historic samples of the different constituents that we identified 25 years ago, and the materials all maintained, kept in the campus planning department. They're used so we have a standard for all of the pavement. The pavement is formed with wood forms, as you see here. The alternating squares are placed, so we do one color, either a red or a gray at one time, wait for the formwork to dry, remove the forms, put in the building paper between them, the tar paper, and then remove it and place the other ones. Here you can see the honing that happens after the concrete is cured, and then the final washing. This is the actual installation where we start with a drain rock to stabilize the area that's going to be repaved. And then it's compacted. And then finally, over here you see the formwork. You see the alternating squares. It's surfaced carefully. And here you can see this is what it looks like when it's first placed. We broadcast the aggregate to get the color just right to match the original, right there in the red and in the gray. Okay. As you alternate, or you put in one color at a time, and you remove the wood forms, which are 1.5 inches thick, and then those pieces of pavement that you've put in become the form for the next round. So you have to remove the forms so that the next color can come in. The paper allows each individual piece of pavement to move independently. And of course, we found over time that there's movement, natural movement, either because of the clayey soils or because of settlement. And rather than producing cracking, we get a little bit of movement between each pavement because they're independent of each other. We do the mixing essentially how it was done originally. So when we took up the pavements many years ago and examined them, we found that they were actually done in 2 pours. The first pour is about 3 or 4 inches thick. It's just a gray concrete. That is put down first. And then the color coat, which is about, or the color layer, is about 1 inch thick, is put next. And it's done, the mixing and everything is basically, it's the traditional way that it was always done. The only thing that we do different now is that we have a little bit of chopped fiberglass, and that helps in the shrinkage and reducing the hairline cracks that develop over time. So it's cement, it's the aggregate, and it's the sand, and then it's the water. And then it's all mixed in a cement mixer, right? Exact proportions every time is the same. And then when it gets to the right consistency, then it's placed into the forms, just like most concrete is done. We add a pigment that is, it's a mineral oxide, so it comes from the ground. And we did make a mistake one time. We lost the supplier for one of our mineral pigments. We ended up trying to use a liquid pigment, and that did not produce the right color. And we had to replace those pavers. So what we found in this particular type of work on reproducing historic fabric is that going back and doing exactly the way it was originally is the way to match for the whole quad. All right, so there's not an inconsistency.
Hi everyone, thank you for joining us today. This is Juan Lopez here. We're going to give you guys a quick illustration of how the paver is actually installed during a real operations. And basically the paver is made out of 4 inches of concrete, right? And we place a stainless steel nut, 1/2 inch stainless steel, to differentiate the original pavers with the new paver. So that way in the future, someone can come by with a metal detector and figure out which ones are original versus which ones were poured in early 2000s. So we go ahead and do a 4-inch concrete here, and then Juan is gonna go ahead and start installing the color. And the color is about 3/4 up to 1 inch of color. It gets spread out. We do a thin layer first to make sure we got nice bonding. Once he does that, he comes back and taps it, and then he's gonna screed it, right? And the tricky part here, and the most interesting part is, we're gonna go ahead and broadcast the aggregate. And we use 2 different sizes to really give it a natural finish. And once the aggregate has been broadcasted, he's gonna go ahead and trowel it so it's nice and sealed. We let the paver sit, cure for anywhere to 3 to 5 days, just like you see we did here earlier today. Once the paver has cured, we come back and use a wet honing system, right, with a cup wheel to expose the aggregate and give it a natural patina finish that the original pavers have accomplished in the last 100 years. So now that he has screeded the surface, he's gonna go ahead and broadcast two different sizes of aggregate. It's a size 14 with a size 16. That's the size of the mesh. Sifter. I'll place them right here, one.
Clean the edges, some of the edges.
Yeah, clean the edges.
Make it looks clean.
Usa este. Usa este. Quédate los guantes.
Necesito unas ragas.
Quédate los guantes. So he'll start with the bigger size first. Eso está bien. Perfecto. So he's broadcasting at this moment what we like to call salt and pepper. And originally, the red aggregate, right, was integrated with the sand. So now, obviously, we can't get our hands on that sand anymore. So now, what we do is to match the existing color and aesthetics of the paver as close as possible, we have to broadcast each paver with the red aggregate.
Okay, so I'm gonna use the edger.
And what he'll do now is use the edger, close it off, and then seal it. So that way the aggregate, it's locked in inside. And like I said earlier today, once the paver has cured, and that typically takes anywhere from 3 to 5 days, we come back and hone the surface to expose the aggregate with the actual sand. That's part of the color mix.
the rosette that we have right out here. A little trickier. We had to fabricate the forms out of steel, and it was placed in essentially the same way. But what was happening here was we also had to plan for delivery trucks. So we had to engineer this particular pavement so that for the weight, the axle weight of the delivery trucks that would back up here for supplies to the quad. And this is just the process that was gone through: the setting of the forms, the installation of the various colors, the tooling, the leveling of the forms, and then finally the placement. Well, we did have quite a project about a year ago when there was a student protest. And interestingly enough, to the students' credit, they used what they thought would be a material that would not damage the pavement. And it was a chalk paint. So one would think chalk would wash off. Interestingly enough, I think because the chalk pigments were so fine, it really did get into the pores. And it was very difficult to clean. So we went through quite a testing process to take out the tile. This was at the provost's office, in front of the provost's office, building 10. And what we did there is we tested a number of cleaning materials. We tested conservation soaps and cleaners and surfactants. What we found actually was the most effective was a cleaning process that involves a latex type of material that is spread onto the surface and is let cured. It remains rubber in a rubber state, and then you pull it off, and the stain comes with it. And that's what we did to all of the stained pavers that were over at the provost's office. Well, I think the most interesting part is the original project we did, and that was underneath the four corners. People have called them different things because they're kind of a unique form: ziggurats, small pyramids. In the 90s, there was staining underneath them, and it was a reddish-brown stain. And most architects and conservators and engineers that work with buildings, you look at a building and you see orangish, brownish stain, and you say, it's reinforcing bar that's corroding inside. And so that eventually is going to disrupt the masonry, and it's going to be damaging to the building. So we decided to do some investigation. I came out in the early morning, and the craftsmen were up there, the masons were up there working on one of these pinnacles. And I drilled a little hole in between the mortar joints of the cast stone. And I pulled the drill bit out, and it seemed a little moist. So I said to the guys, get underneath. Why don't you get underneath? And this is before cell phones. Get underneath there, and I want you to drill a hole up from underneath and let me know what happens. I got back to the office in San Francisco, and I got a call. And the mason said to me, well, we did what you told us to. We drilled a hole, then we had to attach a hose, and that feature has been draining ever since. It was completely filled with water. So those four features, those ziggurats that you see on the Hoover Tower, had all retained water. I then said, I called the university and I said, well, we need to cut a hatch so we can get into there. They cut the hatch, and what we found was that the stain was not ferrous. It was not being caused by steel. It was actually the wood form boards that were left up into this confined space, this space that was not open in any way to the outside, and water had been seeping in through the mortar joints, and then the wood had been deteriorating and seeping out, and that's what the staining was. So we got rid of that, and we solved that part of the staining on Hoover Tower. As far as maintaining this campus, honestly, I think the program that is in place now, as long as it is maintained, the campus will be in good shape. It's following all the proper procedures in the preservation of cultural resources. Everyone at campus planning is doing a wonderful job. Zones are sensitive to the historic fabric. It's a very different paradigm than when we first started. And I can't say enough for it, because it really recognizes really the most advanced thought in architectural conservation that we have today.